Welcome back, ladies and gentlemen. This should be, hopefully, another quick video. It's going to take place on page 20 of your notes, and it's about molar volume. So we've done molar mass, we've done moles to particles, now we're going to do moles and volume. Realistically, this one only comes up every once in a while. Molar volume specifically talks about gases. All right, so as it says in your notes here, particles have mass. I hope you know that. And we have worked with this for some time now. Something we haven't seen is that particles also take up space. You know, there's a reason why stuff takes up space. So this means there is a volume. The volume of a gas is connected to the number of moles. Other things also have a connection between their volume and the number of moles, but that connection goes through a term called density, which you guys learned about in grade 7 originally. But for our purposes, we're just going to talk about gases. And what that means is that if you've got a gas, you can convert directly from the amount of gas, the volume of gas, right, how much space it takes up, and the moles of gas. So, like any conversion, this is going to involve a conversion factor. Because everything that we're doing when it comes to conversions follows the same conversion matrix, right? Have, want, lose, gain. Brackets, equals. Again, though, the question is, what is the conversion factor? The conversion factor that goes in here is that there is 22.414 liters for every 1 mole. Usually this gets truncated to just 22.4. 22.4 liters seems like a really weird number, and it is. It's not a nice round number, it's not a simple number, it's not an easy number, but it's a number. And it's a number that is, generally speaking, going to be true. Now, I've got here a prop. 22.4 liters is basically the same size as this cube. Now, there are some stipulations on this. This 22.4 liters only is equal to 1 mole if I can get the right side, you are at what's called standard temperature and pressure. We'll talk more about this in the gases unit, which is like 2 units away from us still. But standard temperature and pressure is 0 degrees Celsius and 101.3 kilopascals. That's Earth's atmosphere. That's what that is. That's Earth's atmosphere. So what I'm saying is that if it's like freezing out, right, it's below 0, it's 0 outside, and the atmosphere of the Earth still exists, you're at standard temperature and pressure. So for example, this 22.4 liters that I'm holding right in my hand is how much 1 mole of oxygen or carbon dioxide or water vapor would take up. So if I were to exhale outside and it was 0 degrees, and I make that nice steamy cloud, if I were to fill up a container this big, it would be 1 mole. Which of course means, since moles are connected to Avogadro's number, that it would be this many particles. So yeah, this is the basic idea. You'll notice that it's like pretty much, like maybe 3 times the size of my head, give or take. So it's a pretty big amount of stuff, and that means that, you know, for example, I could take this box here and I could line it up along the room, starting in one corner, and just stack it outward all the way across the room and all the way down, and just map out how many of these boxes are in one classroom. And that would tell me how many moles of air there were for us to breathe inside the classroom. So obviously this is good. Like, there's a lot in here, which is important because we need a lot of air to live. But that's also why improper ventilation is important, right? Because if there was no air coming in here, eventually we'd use it up. So this is the key, right? At 0 and 101.3, which only really is going to come up a lot when we're talking about, what do you call it? Gases unit. Also, in your notes, it says not 101.3 kilopascals, it says 1 ATM, or atmospheres, because 1 atmosphere is the amount of pressure that Earth's atmosphere provides. So we made a scale to measure the pressure on Earth by calling the normal pressure on Earth 1, because we were lazy. I know. Why the 101.3? Because it turns out that sometimes we do things that don't involve Earth, like other planets, or maybe the inside of some kind of special device that we've built. Either way, here is our 1 mole of gas. But let's do some math with it, because that's what we've been doing in this unit, right? We're going to turn this into some math. So if we see here, we've got an example. Calculate the number of moles in a sample of gas that has a volume of 3.72 liters. All right. So let's use green. Sure, why not? So we've got 3.72 liters of a gas. We don't know what gas, but it doesn't really matter, right? For the purposes of molar mass, we would care. We'd have to pull out a periodic table. We'd have to figure out how heavy that particular gas is. But for the purposes of volume to moles, don't care. Brackets, we want to get rid of liters. We want to get moles because we're looking for moles over here. Well, 22.414 liters is 1 mole. And that's it. That's all we have to do to set this up. And then we just type in our numbers. 3.72 divided by, or times 1 divided by 22.414 equals 0.17 moles of gas. It's not a lot, I know. And 3 liters seems like a lot of stuff, right? Like if I tell you to go down to the 7-Eleven, the supermarket, whatever, and grab 4 liters of milk, that's pretty heavy, but 4 liters of gas isn't very much at all. And that just comes down to the simple fact that gas is pretty light. That's why it floats. Well, not all gases float, but gases are light. We'll talk more about why gases are light and how they work in the next unit called Physical Properties of Matter, and then especially in the gases unit where we talk a lot about gases because it's the gases unit. You get it. You understand what's going on here. I don't need to explain it. So we have another example. 1.02 moles of carbon monoxide gas. So 1.02 moles of carbon monoxide. We want to know the volume, so the liters of carbon monoxide. Set up our conversion matrix. We want to get rid of moles, so they go on the bottom, and we want to get liters. So moles are down here. 22.414 is my volume. If you use only 22.4, your answers will be fine, right? Like here, I'll show you. We'll do this first one using 22.414, and then I'll do it again without the 14 bit. 1.02 times 22.414 equals, the answer I get is 22.86. Now, if I change it so I get rid of the 414, I get 22.85. So the difference there is pretty small and only really matters if I'm dealing with very small quantities. So if you use 22.4, that's fine. Go right ahead. No big deal. Anyway, that's kind of it. Like, it's the same basic thing we've been doing every one of these times. The difference is just we're using a different conversion formula. The big problem isn't necessarily doing each of these individual steps, right? So page 20, page 21, you'll see that you've got some practice problems that you can do. Page 22 will show you a nice little relationship between different things. And you'll remember in the last one, we talked about the fact that if you want to go from here, particles to mass, or mass to particles, you can't go directly there. It always has to go through the mole in some way. Same is true with volume. So this little T-chart here, or this triangular kind of shape here, is pretty critical, and that's kind of what you're going to be focusing on. And what you're going to see over the next several pages here, page 23, 24, 25, and 26, is just tons and tons of practice with all of these things mixed together. Well, I'll ask you stuff like, I'm going to give you a number of liters of gas and ask you how many particles of gas are there. I'm going to give you the number of mass of a gas, and then I'm going to tell you to turn it into the liters of gas. So it's just a multi-step process. You convert one, then you convert the other, call it a day. Okay? Another short one, I know, nothing too fancy here. Hopefully these things are coming together pretty nicely. Hopefully we aren't having too much trouble. Again, the hard part with this isn't necessarily doing the conversions. I mean, typing in the scientific notation can be a bit of a pain. The hard part is usually just making sure you're doing the right conversions. Okay? But just remember, conversion matrix, keep that in mind, and then you guys just need to know your various conversion formula or your conversion factors, right? This one here, kind of expecting you to know it. The molar mass, I'm not expecting you to know that. You have a periodic table, you can look that one up whenever you want. Avogadro's number, expecting you to know that. So do what you can, of course, to try and memorize these terms that you need, and just practice. A lot of practice will basically just put these in your brain without you having to spend any other effort doing it. So I'm going to leave it there, ladies and gentlemen. Another quick one, and see you with the next video.